In this documentary series, I will be focusing on the geochemical and mineralogical makeup of celestite, sometimes called celestine, which is a mineral crystal. But first, it is very important that I explain the origin of the word celestite. The word celestite is derived from the Latin word celestis, meaning heavenly, referencing its sky blue hue or color, because from a metaphysical point of view, celestite is a mineral believed by some to be a bridge to the celestial or heavenly and angelic realms, promoting calm, clarity, and spiritual connection. However, on the other hand, for geochemists and mineralogists, celestite is a mineral crystal, which is chemically composed of strontium, sulfur, and oxygen, with trace amounts of other elements, with the chemical formula SrSO4, which is strontium sulfate. Celestite is commonly associated with sedimentary deposits through the interaction of strontium-rich fluids with gypsum or anhydrite, or as a primary precipitate in hydrothermal veins. The geochemical environment, including temperature, salinity, and the presence of other ions, influences its crystal formation and purity. The blue color of celestite comes from trace impurities, natural radiation, and crystal lattice defects. However, while it is famous for its light blue color, celestite can also be colorless, white, pale green, or pale brown. Now here is a question: how exactly is celestite crystals formed or grown in the natural geologic environment? Well, it starts first with the initial stages of crystal growth called atomic nucleation, which in the case of celestite is an epitaxial process that occurs from supersaturated aqueous solutions of a precursor mineral like barite, which is barium sulfate, with the chemical formula BaSO4, or anhydrite with the chemical formula CaSO4. This process involves strontium and sulfate ions overcoming a critical supersaturated threshold, allowing them to align on a template surface. Now at the atomic level, this can happen on cleavage steps of a substrate like barite, where ions form into two-dimensional nuclei before coalescing to form a continuous layer. Or in other words, celestite often nucleates on existing mineral surfaces, such as barite or anhydrite, taking advantage of their crystal structure to form a new aligned crystal. Okay, so now, let's talk about the various crystal habits of celestite crystals. Firstly, celestite often occurs as well-formed, thin to thick tabular or bladed crystals, sometimes with pyramidal terminations, exhibiting a distinct orthorhombic form. It can also occur as fibrous veinlets, granular aggregates, and sometimes as large lamellar or massive deposits. Celestite crystals may show striations or parallel lines on their surfaces. In addition, celestite often form into clusters of pointy gem-like prismatic crystals. Celestite can sometimes be thermoluminescent, meaning it can emit light when heated after being exposed to radiation. Alright, so let's now talk more about the geological environmental conditions required for celestite crystals to grow in. So the chemical element, strontium, that forms part of celestite can be sourced from the breakdown of organic remains, such as coralline algae or other terrigenous materials within sedimentary basins. Fluid inclusions within celestite crystals indicate formations, temperature ranging from 210 to 390 degrees Celsius. Diagenetic processes, including the interaction of surrounding sediments and organic matter, influence the mineralogical nature and chemical composition of the deposit. The associated minerals of celestite include sedimentary minerals like gypsum, anhydrite, and halite in evaporite deposits, as well as dolomite, calcite, and sulfur in limestone and sandstone, and in hydrothermal environments it can be found alongside fluorite, barite, and various lead and zinc sulfides. So based on their associated mineralogy and formation, celestite can be classified as pure, calcareous, or gypsiferous. So now that the geological environment required for celestite is explained, I can now explain how celestite geodes are formed. Firstly, it occurs when strontium-rich groundwater or hydrothermal fluids fill a cavity or void, replacing other minerals or precipitating directly. This process often takes place in sedimentary rocks like limestone and dolomite, where the strontium-rich solutions dissolves less soluble minerals, such as calcium sulfates like gypsum or anhydrite, and then deposits celestite or strontium sulfate. The celestite crystals grow inwards, lining the cavity or void, and creating the characteristic crystalline interior of a geode. When a geologist, geochemist, mineralogist, or even a crystallographer finds or discovers a celestite crystal in the field, it may be an indication that the area was once covered by a shallow evaporating sea, which provides great insight into the prehistoric environments that existed millions of years ago. I have a perfect example of a celestite geode in my personal collection, to which I did 2 short videos on YouTube about, called Celestite Geode, a strontium sulfate crystal. I will put the link to that video in the description and in the comment section below. And since I spoke briefly about barite in this current geoscience series, for our next geoscience episode or series, I think it's most appropriate to do a video discussing and explaining the geochemistry of barite crystals. So keep that future geoscience video close in mind. I have also done a short video displaying a specimen of a barite crystal cluster to be released on the Soil Mineralogist channel. So remember to look out for those future geoscience episodes by staying tuned into the Soil Mineralogist channel.